Good morning, everyone. Today we talk about another applications of linear programming or prescriptive analytics. So the first application is goal programming. It's for the cases that you have multiple objectives and also sometimes your objectives are contradict with each other. Let's look at this problem. It's about Myrtle Beach Hotel expansion. Davis McCune wants to expand convention center at his hotel in Myrtle Beach in South Carolina. The types of conference rooms being considered are a small conference room has 400 square feet and unit cost is $18,000. Medium one has size of 750 and unit cost of 33,000. Large conference room has size of 10-15 square feet and also cost of 45,150. Davis would like to add 5 small, 10 medium, and 15 large conference rooms. He also wants the total expansion to be 25,000 square feet and limit cost to $1 million. So in this case, if you just looking at Davis' plan, and if you want to have 5 small rooms, 10 medium, 15 large rooms, if you do the calculations, you will be over budget, and also the square feet area would be more than 25,000. So budget, I think, is 1,097,000, and a square feet would be a little more than that. So as you see, if you want to have budget or area, if you aim that budget and area, you won't have those number of rooms. Also, if you want to keep those number of rooms, you will be over budget, and also the area would be more than 25,000. So in these cases, we may not want to achieve what exactly we are looking for, but we want to have a minimum deviation. So let's say if you want 5 small rooms, maybe 6 or 4 is close to what you are looking for. Maybe for 10 medium rooms, 9, 11, maybe 12 would be close, or for 15, maybe 13, 14, or 16. Also for budget and area, maybe something around them would go good for you. So in these cases, we want to have the minimum deviation from our initial goals. I give you a little bit to think about the problem, then I get to the solution. It's the last week, 14. So far we have seen we cannot have hard goals, or we cannot achieve everything that we are aiming. In this problem, we have soft goals. So we just want to achieve as close as possible to our initial goals. Let's look at the formulation. So it seems on top of the decision variable, which is number of rooms, we also should look at deviation. So maybe we should decide how much deviation from the initial goals should we have considering our decision variable. So it seems we might have another decision variable that takes care of deviation from initial goal. There's different ways of formulating such problems, but here I'm showing one of them. So again, we use abbreviation. So S stands for small rooms, M medium rooms, and L large rooms. And we know they are the most intuitive decision variables that comes in our mind, because we should decide about how many rooms of different configurations we might look for. So again, these are our 5 goals: 5 small rooms, 10 medium, 15 large rooms. Budget expansion, the expansion area 25,000, and the budget 1 million. 5 goals. So look at how I formulated the goals. So for S, which stands for a number of small rooms, I added plus deviation and minus deviation. So if you end up making 3 small rooms, so DS plus would be 0. So you didn't create more, or you didn't have overbuilt. You just have DS minus. So DS minus would be 2, and S would be 3. So 3 plus 2 would be 5. What if you have overbuilt? So if you have overbuilt, you don't have DS minus. So let's say you may end up making 7 small rooms. So S would be 5. So S would be 7. DS plus would be 2. So 7 minus 2, 5. So because if you make 7 small rooms, means you have 2 overbuilt. TS minus or TS negative would be 0. TS plus would be 2. 7 minus 2, 5. So having said that, we add deviation variables for each goal. So for number of small rooms, medium room, large rooms, even for area, we have overbuilt square feet, underbuilt square feet, and over budget and under budget. So here, on top of deciding about our initial decision variable, we should also decide about how much deviation we are looking for. I wait a little bit in case you have questions, then I just go one step further. So there's another rationale because why for deviation consider 2 variables. Because let's say if I just, for example, for S, which is a number of small rooms, I just, let's say, consider VS. So it would be S plus VS equal 5. So if you have overbuilt, VS would be minus 2. If you have underbuilt, which let's say if you make 7, VS would be minus 2. If you build 3, VS would be 2. So in such a case, when you have overbuilt, like here, you have your S would be minus 2. And mathematically it's correct, but we are using linear programming. In linear programming, all of the values should be positive. So because in the methodology, we are limited to just positive variables. So I couldn't just add one variable for taking care of variations. So I had to find one way to just avoid having negative values. It's the only reason. So we did a little extra work having extra variables to take care of variations, but still we can use the methodology which is embedded in your Excel solver or Lingo. Okay, so now our objective function is a little different. We are looking for minimizing our deviation. So each deviation is, let's say it's a S, DS plus, DS minus for budget or cost for all of them. So for cost, instead of DI, you should have DC plus, DC minus, and same for other decision variables. So we are trying to minimize the variation from our initial goal. Ideally, this objective function should be 0. If we have 0, or we end up having 0, it just means you haven't deviated from your initial goal. All of them, the overbits and underbits of 0. So you gain your you achieved your initial plan, but it's just ideal case. So here, this objective function never will be 0, because if it's not possible. So if you make SL and SML, which is sum of small, medium, and large rooms, equal your initial plan, you would be over budget and over the area that you have limitations. Okay, so having said that, in here, we put all of the deviations together for area, for budget, and number of rooms, which are not mathematically correct because they are different dimensions. So you cannot say, let's say, $200 over budget plus, not 200 is very low. Let's say 100K over budget plus 2 rooms plus 250 square feet. You cannot just add them up. They have different units. For being unitless, we divide them by our goal. So deviation divided by goal, make them unitless. So in here, which I have minimization of summation of D minus or underbuilt and plus overbuilt divided by goal. So the value would be coefficient of deviation. The value won't be dollars or area or number of rooms. So the value of D plus D minus divided by your goal would be the coefficient that shows how much you are deviated from your initial goal. Questions so far? Okay, on top of that, you might have different ideas about deviations. For example, maybe for you, deviating from cost is not a big deal, but deviating from number of rooms is a big deal. So you can add add some coefficients. Let's say for you want to achieve very close to, let's say, 5 small rooms. So you give a big coefficient to the deviation. So adding a big coefficient to deviation and considering the fact that we want to minimize it, your objective function try to minimize the deviation because it has a very large coefficient. Even a small deviation from number of rooms make this objective function much larger. Having said that, so we also add giving some weights to our to different deviation because of their importance. Sometimes overbuilt is a big deal for you. You give a large coefficient. Sometimes underbuilt, maybe it's not very important. So so you give a lower coefficient to your underbuilt deviation. So at the end, it is our objective function. So we are looking for deviation from our initial goal. We divided by their the goal that we have, and we gave different W's, which stands for weight. And these weights are arbitrary. So sometimes in certain industries, you should ask from people who are working there, so they might have a better idea how much weight is should be given to each deviation. But generally speaking, if you don't have any idea, maybe you just put 1. So you give 1 to all of the weights. Okay, so let's look at the solution here. Also wait a little bit for you guys to just think more in case you have questions, then we get to the solution. By the way, I'm still using Excel for some problems because I just want a skill that I want you guys to learn, and sometimes in future might be useful for other applications, but in your final exam, you don't have to use Excel, just Lingo is enough. And Lingo is much easier, so you just type whatever you see here in Lingo and it gives you the answer. Okay, so here blues are decision variables. Blues and yellow has the formula of each goal. So for example, first one, just look, I'm multiplying this row by row 4. It just means decision. So the coefficient M and L are 0 because this is for first goal, which is number of small room. For S is 1. So S times how many small rooms we want to make? Plus deviations. So D plus, so D minus minus D plus. Same for second. So we are looking at number of basically medium size up to how much we want to make from medium plus minus overbuilt and underbuilt. Same for large room, square feet, and also for the cost, we are taking care of decision variables and also deviation from ideal goal. So later on, this yellow cell should be equal our goals, and the reason, the rationale is here. Sorry, my mouse has some issue. Yeah, for some reason my mouse doesn't help. So the yellow cell are the formula on the left side for each goal, small, medium, area, and budget. And these numbers, and 5, 10, 15, 25,000, 1 million is the right-hand side as the goal values. Also, I put some arbitrary weights. I just randomly put some weights to see what happens. So you can just pick any weight that you like. Here, I didn't know what weight should I put, so I just randomly put numbers. But again, if you don't have any idea, maybe you just put 1 for all of them. This is my objective function. So the formula is very complex. Maybe it's hard to explain over Excel, but it's basically I just reproduce this formula here. Weight times deviation divided by outgo. It might be a little hard to explain here because it's very complex. Anyway, so let's look at the solution. Data solver. So first of all, F16 is my objective function, taking care of deviations. Then I have 2 sets of decision variables. First are fourth row, which is my initial decision variable, also a large blue rectangle, which is my deviation decision variables. Also, I'm saying that fourth row, which is initial number of rooms, should be integer. Doesn't make sense to have, let's say, 4.5 rooms or 10.3 rooms. And also, P7 to P11, which is this yellow cell, should be equal values on the Q column. Press solve. So we end up having 5 small rooms, 10 medium rooms, and 13 large rooms. Our deviation would be 0.27, which is the weighted deviation. So if I go back to the problem here, we couldn't achieve 15 rooms. So 5, 10 is achievable, but for having minimum deviation from cost and area, we should end up having 13 large rooms. And again, they comes from also these weights that I picked here are contributing to. If you change the weights, maybe you end up having different answers. So I wait 1 or 2 minutes in case you have questions, then I go to another application of linear programming. So if you want to study a little more about goal programming, I put two optional readings. I think not just one. So goal programming from book. So I copied from a textbook and put some more reading about goal programming. This is optional, but in case you're interested, please read this PDF file. Okay, one extension of the transportation problem is max flow or flow problems in general. So there's some similarities on how you solve this problem, but also they have their own unique characteristics too. Okay, let's look at this problem. The graph represents various flows that can occur through a sewage treatment plant with the numbers of arc representing the maximum flow in terms of sewage per hour that can be accommodated. Formulate an LP model. So LP, again, is methodology behind the prescriptive analytics, which stands for linear programming. Formulate an LP model to determine maximum tons of sewage per hour that can be processed by this plant. So might look a little complicated. You're sending sewage from number one, or I mean, point 1 to point 7. Since it's a sewage system, you cannot have any, you cannot accumulate any sewage on each point. They are just connections. So, for example, everything that comes to point 6 should go out, or same for point 3. So this is another one difference from here, from this to transportation problem. In transportation problem, you have some supplier and demand points, and you send from supply to demand. Here, still it seems you're sending from one point to another point with some certain constraints. Still, we can formulate how to maximize the flow, which comes from point 1 to point 7. But for such a problem, you can find other creative ways to make your life easier. So let me show you the solution if I have it here. Okay, in this problem, we add an imaginary link from 7 to 1. Instead of saying, and if you connect 7 to 1, now you have a loop. Instead of saying that I want to maximize flow from 1 to 7, at the same time, we can say I want to maximize flow from 7 to 1. Since it's flow, if you maximize the upper branch, it's equivalent to maximizing the lower branch. So our objective function should be much easier right now. Also, since it's an imaginary line, we don't want to have any constraints. So maybe instead of we can have a very big capacity, and we can just say this virtually this line shouldn't have any capacity cap. So any flow that comes to its link should go from 7 to 1. So other than this creative way of solving, the remaining should be pretty similar to previous problem. So everything comes to each point should go out. So in and out flow, their summation should be 0. And the second constraint would be the link capacities. For example, from 1 to 3, the capacity is 9. You cannot send more than 9. So you just have these two constraints. So in here, still blue cells are decision variables. It just shows how much flow we want to send from one point to another point. For the 1 to 2, 1 to 3, up to 7 to 1. On the left side, we have capacity of each link. For 7 to 1, I put 999. It just means a large number. For mathematics, I cannot write infinity. I just put a very large number, which practically is infinity. Okay, so on top of that, let's look at the first, and the yellow cells are for still the cells that I put formulations. For example, from the, if you click on the first one, you see I said coefficient of 1 to 2, 1 to 3, and 1 to 7 are -1 because they are outflow. Coefficient from 7 to 9 is 1 because it's inflow. I'm just saying that I don't care how much you send, but at the end, summation of inflow and outflow should be 0. It's the reason in the next row I put 0. Same for point 2, 3, 4, and 5. Let's look at 5. In point 5, you have 2 inflow from 3 and 2, and 1 outflow to 7. So from 2 and 3, you have coefficient of 1. From 5 to 7, you have coefficient of -1. It just means, and this formula takes care of their summation. Summation of inflow and outflow should be 0. That's it. So again, I go to the data tab. First solver. So here we are going to maximize D17. So D17 is a flow from 7 to 1. The virtual link with that T end, because we know if you maximize that link, it's just equivalent of maximizing the parallel link, which has several nodes. So decision variable D5 to D17, the flow that we are going to assign to each link. We have two constraints. The first, D5 to D17 less than C5 to 17. It takes care of maximum flow capacity of each link. The last one, G18 to M18, yellow cells should be equal to G19 to M19. So inflow and outflow should be equal. Let's solve. Yeah, this is the answer. So as you see, if you look at D17, the answer is 24. It's the maximum flow that you can send from 0.7 to 0.1, since it's parallel to the upper branch. So it's also equivalent of maximum flow that you can send from 0.1 to 0.7. I just wait a little bit for your questions, then In case there's no question, I'll go to the next problem. Okay, let's look at the next problem. So this is a transportation problem. You have two supply points of 1 and 2, which they send, they have capacity of producing 100 units each. And also you have two demand points with a demand of 75 and 80. Can anyone spot a possible issue here? So also on each link, you have UB, which stands for upper bound capacity. So you cannot send more than that capacity on each link. Okay, so what's my total demand? $80 plus 155. So let's say how much I can send on each link. So first link has a limit of 40 from 1 to 3, 35, 1 to 4. So if you just sum up the link capacities, is 40 plus 35 plus 35 plus 30. So it is 140. So even in the best case scenarios, you cannot fulfill the demand on your demand points. It's the reason in the second sentence, I said, try to meet the demand. So we cannot fulfill the demand for sure, but we want to deliver as much as we can. So we want to maximize, basically, we want to maximize amount that we can send. Here, maybe it looks easy for you because you can just with bare eyes, maybe you can look at the demand and capacity and just subtract and even manually find a solution. But we want to look at more systematic way of solving such a problem. Then you have several nodes. Here with 2 nodes, maybe even you don't have to use a prescriptive analytics. Let's solve it through Excel first. So in here, I just do it with our previous knowledge. So I said, okay, so we have some constraint here, which are highlighted. So we cannot send more than 100. We cannot basically, we should provide 75 and 80 demand here. Also, we have some decision variable which associated to capacity. So our decision variable should be less than our capacity. If you look at the solver, for some reason my Excel is very slow. Yes, so I'm saying that minimize G15. Here, G15 is just multiplication of decision variable times cost. Yeah, so let's just wait a little bit for myself. So summation of decision variable times associated cost. So in the solver, I'm just saying that, okay, G15 is my decision variable. I'm going to minimize the cost. So G15 is my objective function. G7 to G10. So F7 to F10 is my decision variables. I can first constraint, which is F7 to F10, that's an H7 to H10, is taking care of my capacity constraint. The second one, which is J11 to M11, it equal J12 to M12, take care of my supply capacity and also demand constraint. I press solve. Unfortunately, so as you see, look at the bold sentence. Selva could not find a feasible solution because if you might remember, we had some visualization approach. So we visualize the constraint on a piece of paper. So sometimes when you want to find a common area which works in all the constraints, you end up having no area or no feasible answer. So if you recall in that case, if your constraints are contradict with each other, maybe you don't have any feasible area to find its feasible solution. So what can we do in these cases? Again, here you could you need to use some creativity. I'm adding visual dummy points with a very large capacity and also very expensive cost. So in this case, with this adding constraint, if point 1 and 2 send something to that dummy point, it will be very expensive because the cost of each unit is $999. Again, I couldn't put infinity value. I just put a very large number to work as an infinite number. So in this network, if I want to minimize the cost, I should send as much as I could to the right side and the minimum part on the left side. Because if we keep adding, if we send more, if we cannot send all of our supply, we should have sent something to the left side, which is very costly. Linear program has internal intelligence. So in this case, when you want to minimize your cost, it just deliver as much as it can to number 3 and number 4, because it want to avoid the huge cost of delivering to the dummy points. Then the problem here is not fulfill the demand, just try to meet demand. So with these dummy points, we basically try to fulfill the demand by just maximizing whatever we can or whatever we can deliver to that demand points of 3 and 4. So in this case, I'm adding two links. So if you look at the decision variables, I have 1 to dummy and 2 to dummy. These are the products that I couldn't deliver to number 3 and 4. They have a cost of $9.99. It's just for having very expensive. So the remaining is same. So if you look at the constraint, so I have 2 for 100 and 100. These are my supply. I cannot send more than supply. I try to meet 75 and 80. And also the demand of dummy point is 999. It just means a very large number. You can put 2,000, 3,000. Just a very large number, which means very expensive and no limit. I press solver. I think. So minimizing L41. Sorry, L41, yes. Yeah, I think, yeah, I just click. Yeah, my solver, my Excel is very slow. I click a wrong location. So my objective function should be G17. Let me just, yeah, maybe Excel doesn't help. I think it's the last problem for today. Hopefully next class, my Excel would help me. Okay, so let me just click again. Yeah, I think it changed. So this is not the objective function. This is the objective function, G7. Okay, so decision variable F7 to F12, these blue cells. F7 to F12, F7, F12, less than capacity. H7 to H12. Also J13 to N13 should be less or equal J14 to N14. So let's just press solve. Okay, I think today maybe it doesn't help that much. So let me just come here. Okay, so as you see, 25 products went to dummy points from 1.1 and 35 units went to 0.2, from 0.2 to the dummy. These are products that we couldn't deliver. Also, as you see, 70 units received to 0.3 and 70 to 0.80. Even that constraint that we have overlinked, we couldn't satisfy the demand, and we have to send some units to the dummy point, and it was the best thing that we could do. And there's an objective function here, but just keep in mind this is not the realistic objective function, because we also multiply a very large cost value for sending from 0.1 to dummy and 0.2 to dummy. In this case, I mean, your decision variables is the values that you need to consider for your plan. So how much you can deliver in point 3 and 4, and how much couldn't be delivered. Since it's the imaginary point, those units would be stay in number supply point of 1 and 2. Okay, so let's look at the big picture that we have in this course. So in this course, we spent almost 30% on descriptive analytics, visualization. So you learned Tableau, Power BI, and also you learned basics of visualizations. It has some overlap with predictive analytics and prescriptive. So for predictive, maybe it helps you for data preparation and understand what's going on. Sometimes you have some dummy variables. Sometimes it might be some issues in your data that you find by visualizations. For example, outliers could be easily picked by visualizing your data. All of them has some overlap. So with descriptive analytics, you find the current situation. With predictive analytics, you can predict what could happen in future. And with prescriptive, you can find the optimal solution given the current situation. So we learn Tableau, Power BI, Excel Server, KNIME, but also we emphasize on professional communication. So we have every year we have so many good students with very good technical skills, but end up not having the best possible jobs that they could have because they couldn't communicate with employers. They couldn't have good interviews. So it's the reason you had several presentations in the class just as a practice to improve your communication skills. Yeah, hopefully COVID is going away, so good days would come, better job market. So what can you do next? One could have a certification adding your LinkedIn resume. So Tableau provides the best certificate, but is a little costly and also might be a little complicated, but actually is the best Tableau certificate. But you also have LinkedIn Learning, which is free. Also, you can I think you can, after this course, you can easily get the certificate, just have on your LinkedIn. So when recruiters search for your resume, they can pick your information because there's millions of people who are looking for jobs. Human cannot, maybe sometimes connection helps, if somebody refer you, but for most of people, there is some predictive programs. So they run some machine learning algorithms over people's resume data, and they predict who could be the good candidate. After their predictions, some HR people looking at predicted resume, and then they basically filter out the best people. But so first part, the algorithms should pick your CV. Second, you should have good interview. So when they pick your LinkedIn resume, you should impress them. And both of them are very important. So in LinkedIn Learning, having certificates and having on your resume are really helpful. There's some other website, Udemy, Coursera. From the others, I love Udemy. It's to the point. Usually they don't waste too much time. But I'm not a fan of Coursera and edX or DataCamp. They are great, but my taste is different. I don't say they're bad. So because for me, I just want to get some skills. I don't want to spend too much time here and there. But if you love a certain domain, and you want to spend good amount of time learning them, maybe Coursera and edX are also really great. Yeah, so these are the certificates that I recommend to have on your resume. So Power BI, Python, R, Hadoop, and PySpark. So Hadoop and PySpark are mostly for students in the business analytics major. they are one of the last courses that they take with me. It's actually the most difficult course in the program. But having the certificate is very useful. Do you guys know Ashish Shashank Gupta? Yeah, his first job was doing some analytics with Hadoop and Spark, and now he has a really good job in Boston Consultancy. There's I forget the we call it Boston Company, but there's a consulting BC, yeah, BC Group. So for your project, I mean, next week, please do presentation. I might teach a little bit of, I'm not sure, but some of the problems I couldn't teach today because my Excel had issues. If I don't teach, it won't be in your exam. So if all of you present, probably I cannot teach. So would be less problems to study. But even if you cannot present the next week, please don't submit after May 7. Also, I give you a final exam. You can look at the last year final exam here. So you can solve it together, but if I give you final exam, it's an individual problem. You cannot share with each other, but you can work together and just solve this problem, which was for the last. Follow me? Oh, okay. So this is the last year. You can share and help each other, but the final exam is take home, and you shouldn't do it together. So it's not a group assignment. So it's an individual assignment. Anyway, so I send you a link for next presentation. So I look at the people who would be something like a survey. So I look at the order that people said they want to present, and we do presentation on Monday and Wednesday. You don't have to, but I still recommend to present next week. So I might give you some feedback. You fix it and just submit anything by May 7. So I grade after May 7. Questions? Yes?
How long should the presentation be? Like, depending on how many?
Keep it less than 10 minutes. Yes?
So for the feedback, are you only going to give feedback on the PowerPoint, or did we also make changes to the Word report or the files after you?
So if you let's have everything in your PowerPoint. So because I look at the PowerPoint in the class, if I see you didn't do something, I would say, okay, do this or change this part, something like that.
Because we submitted a Tableau file and a Word report last night as well.
Okay.
I'm just asking if you give feedback on that. Can you make
I cannot make feedback for all of the class by next Monday or Wednesday. Maybe I give feedback to some of you, but I cannot set it. I don't have time to give feedback for everyone.
So that would be graded on what we submitted last night.
Pardon me?
Then we will be graded on what we submitted last night.
Yeah. Also, after the feedback, you might also change your last submission. So that's totally fine. So if there is I hesitate to look at it, because after next Wednesday, you might also get back to your submission and change it. Okay, so if there is no more questions, so let me just give you the attendance of today.